Let's start out with some key concepts here. So we're going to talk about our first set operation, which is an intersection of sets. So we've got an intersection of sets. So if you think about the word intersection, on a road you have an intersection, two things intersect, they meet. Well, we can have intersections of sets. So for any two sets, we're going to call it a generic A and B. So A represents a solution set, B represents a solution set. So for any two sets, A and B, the intersection of A and B is symbolized by the following. A, it looks like an upside down U, B. And is defined as follows. Okay, so here we have our solution set represented for the intersection of A and B. Okay, so if you see A with an upside down U and B, it's asking for the following. It's asking for all your values of X such that, remember our bar means such that, X is an element of A and X is an element of B. Okay, so the intersection. You've seen Venn diagrams since middle school probably, maybe even elementary school. If I had a Venn diagram where my left circle represents, or oval, represents set A, and the right oval represents set B, where would the intersection of those two be?
X.
Well, physically in between, right? Okay,
X.
so your X, all your set of X in a intersection would be everything in between. So the overlap, bless you, the overlap of the two. Okay, so key points, you should be able to identify what this notation means. Upside down U means we're talking about the intersection of two sets of numbers. Okay, and if you need the visual of it, think about a Venn diagram, and the intersection of the two sets is what is in the middle. All right, so let's see what that actually looks like with physical sets of numbers. Are you ready? Okay, so we're going to give you two sets. We're going to let our first set A be the solution set of 1, 2, 3, 4. Those are nice numbers. And we're going to let B be the solution set 2, 4, and 6. And you're going to be asked to find A intersection B. Okay, so we need to look for the X elements that are in A that are also the same X elements that are in B. Or, which numbers do they both have in common?
2 and 4.
2 and 4. Does everybody see that?
So how do we write that?
So we would say, oops, I'm in highlighter mode. A intersect B is equal to the set of 2, 4. So we're looking for the numbers that they both have in common. So they both share 2 and 4. So we want to find X such that X is an element in A. Well, 1's an element of A, but is it also an element of B? 1's in A, is 1 in B? No. Scott, question?
Is it always going to be two numbers? Or is it
No, it may not always be two numbers. It could be all of them. It could be none of them. It could be three of them. Okay, so that will change. 2 is an element of A. Is 2 also an element of B? Yes, that's why it's down here in our solution. 3 is an element of A, but 3 is not an element of B, so it's not in our solution for the intersection. 4 is in A, 4 is also in A, so it's in our solution. I didn't hit every element. Here's a 6, but 6 is not over here, so that's not in the solution set. So you're just looking for the numbers that they both have in common for intersections. Okay? All right, so now let's talk about compound inequalities. We talked about compound inequalities in Algebra 2. You talked about compound inequalities in Algebra 1. You may even talked about compound inequalities in the beginning of your geometry class when you were talking about rays and line segments. So if we remember what a compound inequality is, it's when two inequalities linked by a connective word such as and or. So and ors are our compound inequality connective words. So we have something and something, or we have something or something. Okay, we're going to focus just on the ands, because the ands are where your intersections occur. Okay, because we want it to be in both sets. All right, we ready to do some math? Here we go. First compound inequality, nice and simple. X plus 1 is less than or equal to 9, and x minus 2 is greater than or equal to 3. Okay, let's graph the left side first. So what do? I know it's difficult. We're going to subtract the 1 from both sides. So then I would get x is less than or equal to 8. And on the other side, add the 2 to get x is greater than or equal to 5. All right, so let's graph this first so we can see what it is we're dealing with. So make a number line. Put your smaller of the two numbers on the left. So my two numbers are 8 and 5, so I'm going to put 5 on the left, 8 somewhere on the right. Again, I'm not going to be picky about everything in between. I just care about those two numbers. At 5, is it going to be a parenthesis or a bracket? Bracket. And I want to go greater than, I'm going to go in a different color because I can. Let's go purple. Bracket, and I'm going to shade to the right. Right. Good. Okay. Then at the 8, what am I going to put? Bracket or parenthesis? Bracket, and I'm going to shade to the left. Now, because this needs to be an and, I need my solution set to be an element of both, meaning I need an intersection. So where is the intersection of my graph, Maddie?
So your shading wouldn't stay within the two brackets. It would extend.
Well, no, it's going to be in between the two is where I'm going with it. I'm just showing you in different colors why we want the intersection of the two, because I need it to be both in them. So my solution area is...
There are two separate equations, so they would have their, basically, we're combining what would be two graphs into one.
Correct.
And so they would go past the other bracket.
Right, but what I'm looking for is
What
to
in
solve
between each two
for the
brackets.
solution set that is true for both this and this.
So
My purple is just true for, or sorry, my yellow is just true for this. My purple is just true for the x greater than or equal to 5. But I want to find my solution area that is true for both of them at the same time, which is the intersection, which is going to be between the two. So here is your solution area, right?
So the purple and the yellow would extend past, so yellow would extend past purple.
Right.
But
But
we're
since I
focusing on
put
middle
the
set.
compound inequality connector of and, my final solution is going to be what's in between.
Oh, okay, gotcha.
Okay? So now, how do I write that part in interval notation? I think Scott had it. Scott, what did you have back there? What did you have for your solution in interval notation?
I didn't have it, but,
It would be bracket
wouldn't it be bracket 5 and 8?
with another bracket. Perfect. Okay? All right. Okay. All right, next one, number 2. So now we have a little bit more steps involved. We've got negative 3x minus 2 is greater than 5. And 5x minus 1 is less than or equal to negative 21. So we're going to solve it and graph it. Working on the left side, add that 2 over both sides. So then we end up with negative 3x is greater than, oh no, got a fraction. My life is over.
And it's gonna flip the
Yeah.
thing's gonna flip.
Thanks for that reminder,
So
Carrie.
even with these equations, we should keep them as fractions
Yep.
if they're fractions.
Yeah.
Okay.
I mean, unless it divides by 2, so then it works out to be a nice decimal, then I'm not going to care about that.
Okay.
But you can't round 7/3 because that would be non-terminating.
Not fine.
No. All right, other side, add the 1 to both sides. 5x is less than or equal to negative 20. Divide your 5. X is less than or equal to negative 4. All right, let's go ahead and make a graph because for me, a visual representation of it helps me to think about what the solution set's going to be. So I need to find the intersection between those two inequalities. Which is the smallest of the two numbers? Negative 4 or negative 7/3?
Negative 7/3.
Try again. Negative 4, right? We're in the negatives.
Negative 4.
So it's going to be the largest. So negative 4 is on the left. Negative 7/3 I'm going to put on the right. All right, because I can, because I've got fancy technology in front of me, I'm going to do 2 different colors. At the negative 4, I'm going to have a bracket. But where is my graph going to go? My shading. It's going to shade to the left, isn't it? So I need it to be less than. So my purple is going to go to the left. Oh boy, this is different than what we did the last time. Now I'm going to pull out that yellow. At negative 7/3, I'm going to have a parenthesis, and my shading also is going to go to the left. Oh boy, so this is way different than what we just did. The last problem, the intersection was in between the two. Now is where is the intersection?
To the left of 1.
Yeah, so if I need my solution set to be in both, if I had numbers in here, would it be a solution set of the purple? No. So that's not. So my solution set starts here and goes to the left forever. So I'm going to make it red. So my solution area or region is at negative 4, including negative 4 and everything below. So what's that going to look like in interval notation, Carrie?
A parenthesis, negative infinity, and comma, negative 4 bracket.
Good, perfect. That's why that graph is crucial. Because you would have probably looked at this and said, just put negative 4 bracket, comma, negative 7/3, parenthesis, and be done. Devin.
What if the other one was a bracket and the other one was a
For the solution?
Yeah, would it change?
You never bracket
No,
infinity.
I meant for like on the graph.
Oh, if this was a parenthesis, then you would just turn that into a parenthesis.
Okay.
So we
Even if
just,
the other one was a bracket.
right, yeah, even if the other one was a bracket. Yep. Okay? All right, let's do one more of these guys. X plus 2 is less than 5. And x minus 10 is greater than 2. So x plus 2 less than 5, and x minus 10 is greater than 2. What does the left inequality give us when we subtract that 2? X is less than 3. Adding the 10 over gets us x is greater than 12. Okay, so let's graph it, see what's happening. Smallest number is 3, I'm going to put that on the left. Largest number is 12, I'm going to put that on the right. At the 3, I'm going to have a parenthesis, but where's my shading going to go? To the left. At the 12, I'm going to have a parenthesis, and where's my shading going to go? To the right. Ooh, is there an intersection? There is no intersection. So are there any numbers that would be in the solution set?
No.
So what do we say when we don't have any numbers that are in the solution set? There are no solutions. Good. Okay. You can just put no solution. There is no solution interval notation, so just put no solution. Okay. What if, let's pretend this was flipped and my signs went in the other directions. So it went this way and this way. And then my purple went this way. And my yellow went this way. Then where would the intersection be? Between 3 and 12, right? So then it would be 3, 12 with parentheses around it. Good. All right, so we got our ands. Now let's talk ors. Feel free to not rewrite all of this over again. I would just write the part where it has the notation. So this whole section is what I would put in my notes. So now we're going to talk about ors. I should not say the intersection up here. That's not right. So this should say the union of sets. Okay. So now we're talking about the union. The union. So when there is a regular U, not an upside down U, that's talking about the union of the two sets. So if I have A union B, my solution set is all values of x such that x is an element of A or x is an element of B. Okay, so intersection U is upside down. Union is a U. That makes it kind of easy to remember because union starts with a U, and that looks like a U. So now let's think about it as a Venn diagram. If the left oval A represents all the values in A, and the right oval is all the values in B, let's read this. X has to be an element of A. Well, where are all my elements of A? Everything inside that oval, right? Wouldn't that be all my elements of A? Or X is an element of B. Well, where are my elements of B? Everything inside of B, which would be everything right here. So what's your solution set going to look like? Everything in A and everything in B. Okay? So you're going to take everything. So if we were doing an intersection, I was just looking for the elements that were in both A and B. Now when we go back to our sets, so the same A and B's that we had before, here my A was 1, 2, 3, 4. Here my B was 2, 4, 6. The intersection was 2 and 4. The union is going to be every single element in A or every single element in B. So that means I need to list every single element. If they both have an element, I'm not going to write it twice. Okay? So my A union B is going to be the set. And you try to put smallest first and then go to largest. So my smallest number up there is what? 1, followed by 2, followed by 3, followed by 4, followed by 6. So that would be the union of the two sets.
Basically, you add all the numbers together, and you don't add 2 if they're...
Right, you don't write 2 or 4 twice because it happened twice. So you're just writing every single element inside. Okay, so questions 1 through 14 in your homework tonight are similar to this, where they're going to give you a set and you have to find either the union or the intersection of them. Okay, so now let's do the OR compound inequalities. Because this is where your notation is going to get a little bit different. So 6x minus 4 is less than 2x, or negative 3x is less than or equal to negative 9. On the left, what would you do first? Kyle, what would you do?
Add 4 and subtract.
Yeah, that's what I would do too. I would move that 2x over, move that 4 over. So plus 2x gets me 8x less than positive 4.
Then if you slip 4x, it would go.
Oh yeah, I'm subtracting it. Never mind. Thank you. Boop, beep, 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 beep. Erase, minus 2x. Thanks for that catch. So 4x is less than 4, which is a little bit nicer because I don't have a fraction, right? Divide out the 4, it gets you x is less than 1. Or divide out a negative 3. Make sure we flip that sign to get a positive 3, because negative 9 divided by negative 3. Okay, so this is an OR. So now let's make our graph. Smallest number on the left, 1. Largest number on the right, 3. Let's focus on that 1. Parenthesis or bracket. Parenthesis, and I'm going to shade to the left. At 3, I'm going to put a bracket. I'm going to shade to the right. Well, since it's an OR, that means my solution set can either be here or it can be here. So it can be both. Well, not both at the same time. It's going to either be one or the other. Okay, so something from there or something from there. So this is how we're going to do our notation for unions, and this is what's new. Give me this in interval notation, just that purple. What does that look like? Negative infinity, comma, 1 parenthesis, right? Give me the right side in bracket 3, so leave a space, bracket 3 to positive infinity. Now this is what we're going to do in between. We're not going to write the word or. We're going to put the union symbol in between the two, so that I know that it's the union between those two intervals. Okay, sorry Morgan, that's pretty low. Do you want me to rewrite it up here? You got it? Okay, so when you get those ORs, it's going to be the union of them. Now if these signs were flipped, and I was getting everything in this direction and everything in this direction, an AND would be the intersection here, but an OR gives you all real numbers, right? And then we would do a negative infinity to a positive infinity. Okay? You guys have any questions?